Sure. Thanks, everyone. Yeah, today it was hard. It was hard for me to come. I came very early. But thanks anyway for this invitation because I love coming here. There is also a cake, so I mean, what is not to like? There is nice people and coffee and cake, so that's all I need. First, maybe I'm gonna because today is a bit special. I mean, you see, it's just us. Let's take advantage of this and do something a bit more informal. And Flora asked me, she was very clear, asking me to do something that was not too technical. So, and I did my best. So we'll see. But first, I would like to know, maybe because I don't know the other fellows, maybe what is the field you work on? Management, civil engineering, medical science, material science, administration. I mean, I know she's a physicist, so I know she's going to understand everything. And Flora is a physicist, and Marietta is a mathematical physicist, and Karen is a she runs the place, so I know. Okay, so this is a very, very diverse audience. So let me start with oops. Okay, let me start. Wait, this is not working. Okay. Okay, good. Okay. So this is the plan. I'm gonna have an introduction. Maybe it's going to be an introduction. We'll see. My idea was to introduce the topic, and then tell you something about some recent results that I've had with some collaborators. And that's these are three models that are related, and then state the field that we have, the result. But okay, if time allows, we'll get there. Otherwise, I mean, I can also tell you about it during coffee. So as you saw, it's the sort of quantum systems in the title. So I'm interested in quantum systems, and I'm a mathematician. So I'm going to try to, I mean, without being a physicist, I'm going to try to explain a bit this. So usually in a possible world, we don't use to describe our position, or let me say this, my state. It can be my position or my velocity, and you can imagine that we can all of us, if I wanted to make an abstraction of all of us, I could think of us as little points or little particles that can be described with certain properties, like, for example, in which seat you're seated on, and I could maybe draw a grid to say, okay, you are seated in this point in a space with certain coordinates. And that would describe all of your positions, and that would describe my system, my audience. So we're very used to this idea of having a position, a very defined position, and also to talk about the velocity that we have at the moment we're at rest. So the velocity would be zero. But when we go to the quantum world, then this is not, this picture it's fades. We don't have a defined position and velocity. There is a principle, Heisenberg's principle, that says if I know the position of my particle, I cannot know the velocity and vice versa. So that means that in a way there is a part of the information on my particle that I cannot have. And in that sense, well, how do we describe then? What would be the equivalent notion of position of my particle now? And you see, before it was a very fine point in space, now it will be a cloud. And this cloud, I'm going to think of it as giving me the likeliness of my particle being somewhere. And this here picture that you see here is actually a probability density. It's a curve that is telling us where is more likely to see the particle. So I cannot know exactly where the particle stands. It's actually very deep. It's not that I just don't have the tools to measure it. It's just that it really, it's a bit more fundamental than that. I really cannot grasp the position and the velocity at the same time. So the particle really is a bit everywhere. And this curve here will tell me where it's more likely to be, where it's less likely to be. But it can be really everywhere. So for example, here, the fact that this curve is shaped like this and it has a bump somewhere, it's more concentrated near this axis, tells me that the particle is more likely to be around this area, okay, than, let's say, here. And well, this is, as I said, from a mathematical perspective, we write this as, we describe this as saying, well, this is a probability that my particle is somewhere in the line, and it's given by this profile of this function. So, I mean, I'm a mathematician, so I deal with functions. And this whole business today is about studying certain functions. Okay, so now in this quantum setting, I'm going to leave these classical ideas, and I'm going to start thinking of this profile. This is what I can, this is something that I can grasp very well, these curves. And this is what I'm going to study. And this here tells me just that at a certain time, the probability of finding my particle in a certain interval is a number that is between 0 and 1. Because it's only giving me the probabilities, right? There is uncertainty here. Now, as I talk about quantum, we were just talking earlier that quantum is nowadays is a very fashionable word, although quantum has been around since the beginning of 1900s, 1920s, was the big breakthrough in quantum mechanics. Emily here can tell you how this is in the list of fashionable words today. Probably because of people talk about the quantum computer. We are almost seeing the quantum computer coming, and that has a huge. If it's real, if they actually have access to a quantum computer, it's going to have a huge impact in our lives. But okay, let's not go too away of the topic here. And let's just say that quantum is, it's a topic that people are thinking about nowadays. In particular, this year was a very good year for quantum systems, or for quantum mechanics in general, and mathematics too. And in particular for French science, it was a very good year. So the French mathematician, Louis Copin, he got the Fields Medal this year. The Fields Medal is one of the biggest prizes in the mathematics community. It's a bit like the Nobel Prize, but for people under 40 years old. There is another prize for senior people. Okay, senior people are not forgotten in mathematics, but that's called the Abel Prize. But you see, Fields is very popular, and it awards the achievements or breakthroughs in the theory of mathematics. And this year, it was this French mathematician that got the prize because he worked on disorder systems, including quantum disorder systems. He developed what's called a theory of percolation, and he used this to study models in quantum mechanics. And he was able to settle open questions using his mathematical techniques. And then Alan Aspect, maybe you have heard of him. He got the Nobel Prize for Physics this year. He's a French physicist and experimentalist, and he has worked in a lot in quantum mechanics. And in particular, we will see later, he has also worked in what we're going to discuss today, disorder quantum systems. He's an experimentalist, so he designs experiments to show physical properties of the systems. And so for quantum systems, this has been a very good year. A lot of prizes, a lot of media, a lot of visibility. So what we're going to discuss today is my research field. It's one model in this big area of disordered quantum systems, and it concerns the transport of electrons in materials. Now I'm a bit stressed now because there is a material scientist in the audience, so I hope I won't say anything stupid. But so this is what we studied when we want to study the flow of electrons in a material. I mean, this is important because this tells us if a material is a conductor or an insulator. We will be able to see how well the electric current, runs through the material, and this is very useful to know. So if the material is a conductor, that happens. I mean, we call the material a conductor when the electrons flow through the material. We call that we say that the electrons propagate. But it could also be that the electrons do not propagate, or material does not conduct the electric current. And in that case, we call this an insulator. Usually the materials, I mean, we can study it in the lab and classify them. This is a conductor, this is an insulator. Now, what happens when the material has impurities or defects? This can be because you have an alloy, you have different materials, or you have your atomic structure somehow is perturbed. So you say, well, you have defects in your material. Well, Philip Anderson is a physicist, and he was studying these materials, and he observed that if the material, ideally, one would expect it to be a conductor, when one has impurities or defects in material, well, this changes, and actually the material becomes an insulator. And this phenomenon of the material turning into an insulator due to the impurities that are in the material, this is what is called today Anderson localization, because Anderson observed and studied this phenomenon. And he got the Nobel Prize in 1977 for this discovery. And this originated, well, in physics, originated a huge community studying disordered systems and the study of semiconductors. So these are materials that in certain range, under certain conditions conducts, under certain conditions becomes an insulator. Okay, so it's not a full conductor, semiconductor. And this phenomenon of becoming an insulator because of the defects, this is what Anderson discovered, and also mathematics. This kickstarted a huge mass of research around it. Mathematicians, of course, this is what mathematical physicists often do. I mean, not all of them, but some of us, we go after physical theories and try to describe them rigorously. Because if we can describe them rigorously, then we can make abstractions and we can study perhaps other systems that fall in the same category, and then we can have a lot of information on their behavior just by, reducing, let's say, the complexity of our problem and being able to categorize systems and knowing the properties already. So the question from a mathematical perspective is, how do we make this description rigorous? If we put defects in the material, how do we prove that actually electrons do not propagate? And here this picture is, I'm going to explain better what this picture is, but just to have it, to keep it in mind. This question gave birth to the theory of random Schrödinger operators. This is one way of studying this problem of having electrons moving through a disordered material. It's not the only one, but it's a nice one, and this is the one that we're going to discuss today. So let's talk about Schrödinger operators. So we want to study the movement or the propagation of electrons in a material. And one way to do this is to look at the, well, instead of trying to study the electron, I'm going to look at this wave, what we mentioned earlier, that this is we call it a wave. This is the function that is going to tell me where the electron is more likely to be. So if I know the shape of this wave, I have an idea of where my electrons are. So if I have a material where electrons propagate, my wave is going to be something like this. And it's going to tell me, well, the electron can be anywhere with same probabilities. But if it's an oscillator, the wave is going to be like that. So you see, it changes, its profile changes, and it becomes higher in some areas and very, very small in some others. That's telling me, well, the electron is more likely to be here in the center than far from it. So this is what we're going to study. And how we do it? Well, we formalize this by saying, well, this is my function, the function that gives me this profile. This is what we're going to study. It's in some nice space of functions, okay? It's not you don't need to worry about that. And this function, I mean, how do we know its behavior in time? We're interested in the behavior in time. So we talk about dynamics. And since this is representing an electron, we know since the 1920s, that this has to satisfy Schrödinger's equation. And it's this equation, what one has to keep in mind here, actually, independent of what this formula might look like, here we have a derivative on time that tells us how the function is changing in time. Okay, so we're interested in how it changes in time, how it evolves in time, how it behaves in time. So that's why we have a derivative on time. That's what this is telling us. And then we have here a function that acts on my function, on my profile, that is going to transform it. So it's a function acting on a function. This is called an operator. And the way it will transform it is by, here, these are derivatives in space. So it's going to look at, well, how is my wave changing in space? Then there is this term here that tells me how this function is interacting with the environment. Because in the environment, we have to think the electron is moving through a material. So there is an environment around it. Of course, I'm making abstraction of, we have a nuclei, the electrons, jump, and I'm thinking that it's like I'm thinking that it's one electron that it's moving around, which is not true. But this model actually works, and it's giving me, in a way, the behavior of any electron that I take, that I consider in my material. So the Schrödinger equation is telling us, okay, my function changes in time according to certain rules that involve its change in space and its interaction with the environment. And the solution, actually, we have a closed form for this. The function is given by this expression here. So what we actually have to study, so we can get a lot of information from this. I mean, this is already known, but finding the solution is not the end of the problem. Actually, we want to see how this solution behaves in time, in the sense of, will this solution behave like this, or will the solution behave like that? So what will be the profile of my function when I look at it on time? And so in a perfect crystal, we would have the atomic structure would be something like that, very, very uniform, very homogeneous. And then when the material has impurities, we start seeing things that, there are things that are a bit different. but we don't know exactly where they are. I mean, it's a material, we cannot know exactly where the defects are. So we can have several different configurations of the defects and the impurities. And one way to think of this is like, okay, well, I don't know exactly where my impurities are standing, but let's use randomness to model this. Since I cannot know exactly where they are, I'm going to just consider all possible cases. And by considering all possible cases of the environment, I'm actually introducing randomness. I'm introducing disorder. And now you see here, this was the term that encodes the interaction with the environment. So this term here, this is another function, will be random. So here, that's what we call this a random Schrödinger operator. We introduce disorder in the model, and now we have the laws of probability. In this model, we define random variables. We have a probability space. We have the whole structure, the whole probability theory associated to this function. And this is what we call the Anderson model. This is actually what Anderson proposed to study the propagation of electrons in the material. And so now we're going to study this function. Now this here, this H, I replace it with my random operator, and I'm going to study how this function behaves in time. And so here are some examples of the potential. So this is how we model the environment. The environment, we want it to be random. So it might be, peaks and valleys, or in the discrete setting are random points on my space. So here is an observation. So this is the model that Anderson proposed to study this problem. And indeed, people have been able to see this in experiments, that this phenomenon, what Anderson observed was that when my operator is like this, when I have disorder, this function stays localized. What we call localized is that it stays concentrated somewhere. So let me jump here. Oops, sorry, there is some mistake here. My function, this here, will look like this. Whenever I look at it in all times, it's going to be something like that. So it's going to be, if I look at the profile, it's going to be like a bump. And it's going to be higher in some place and very, very small everywhere else. This was observed. So here you can see a visualization from a paper in Nature by Billy. Actually, this is from the group of Alan Aspect in 2008. They looked at matter waves and they studied localization there. And this is what you see. This would be something that is localized, so like this. And this would be something that is more spread out. Okay, here they both look like this, but actually the spreading is here is much, much bigger than here. So that means that this is localized compared to that. Okay, so the idea is to look at this function, see how it spreads in space. And what are the typical results? Is that we see, whenever we have disorder, we see this, or we see that. But there is another mathematical aspect, that this is what we see for the function that evolves in time. But this also implies something for this function here. One can study this from a purely mathematical setting, and this function has associated a spectrum that in a way it's a characteristic of this function, and the spectrum has a certain special type that really makes it stand out compared to other functions of this type. Okay, so this is what we mean by pure point spectrum, is that usually if we didn't have these impurities, this spectrum, whatever this object is, would look like a continuous line. But because we introduce disorder, it's actually like little points, but very, very close together. So it really is different. There is something that changes here. Okay, so maybe now let's see so that you can have a more concrete idea of what localization is. Anderson localization is actually not restricted to quantum systems. It also takes place in classical systems. Wherever you have waves, if you have the wave interacting with something that is random, has a random configuration, you can see this phenomenon. So let's see if we can. Oops, we can start this. Let's see if this works. So I have a video. Wait. Sorry. I stopped sharing, I think.
Yes, you stop sharing.
I'm trying to launch the video.
Yeah, I think you have to do it by stopping sharing and going directly to your presentation.
Okay.
Even if we cannot see your slides.
Maybe. Wait. Let me see if I can make it from here. Maybe I can, no, I can't make it from here. But I can show you this online. I have access to internet here, so maybe I'm gonna do that. Because I think these are very the videos are really very telling. And let me just
Yes, I think you can browse the videos. Can you find the internet?
Give it a try.
Toolbar.
You can minimize that, I think. There. Thank you.
So just pause it before just share the screen. Okay, which is this one, no?
Yes.
Okay.
So I just
I think just use the.
Sorry. Okay.
Screen is shared.
I think it's the screen is shared. Francesca, do you see the screen?
Yes.
Okay.
I can see it works. Yes. Perfect.
That's great. Thanks for that. So here you see a wave propagating in a space that doesn't have any obstacles. There, up and down, you see a wave propagating where there are obstacles, but the obstacles are put in a very homogeneous configuration. And you see, okay, the wave propagates slower, but still propagates. And these are simulations that you can find on YouTube by Niels Berglund. He's at the University of Orleans. He's a mathematician who works in probability theory and physics. And okay, so let's stop this. So you see, and now let's compare the behavior between the uniform distribution here and this configuration that is random. It's a possible random configuration. So here you broke all the symmetry, and we will see how the wave propagates. And you see, no, this is a classical wave. Yes. Yeah. Yes, it's a psi square. Yeah. So you see that here the wave still propagates, but here it got stuck, kind of got stuck in the wave. This is localization. Yeah. So this is the idea of localization, that your wave cannot propagate. If the configuration of your obstacles is not symmetric, in a way it's random, then this is what happens. And the fact that this is a wave phenomenon. So in quantum systems, we have this wave, this function that we're looking at is actually a wave. And in classical, for example, this, I think Niels, he was modeling, putting, how do you call this? Sticks, when you have a beach and you want to, in the sea, and you want to protect the beach from tsunamis. It's not a dam, it's not barriers. You know, you put sticks. You put wooden sticks all over the place. So this just shows you, like, okay, a random configuration of them is more efficient. You know, putting randomness is better than having a uniform configuration. So that's the whole point. Sometimes putting randomness helps. Okay. So now let's go back. Where am I? Let me find the presentation again. Thank you. You're much better at PPT than me. I usually in a math talk, they would, mathematicians would kill me if they saw that I was using a PPT. But I thought, okay, here people are more open-minded, and I'm going to use a PPT. But it's pretty good to hone my skills in PPT. Okay, so this is the phenomenon of Anderson localization. Besides this phenomenon, Anderson also conjectured a transition. So he conjectured that there was a transition from. So you saw that this function that we're looking at is related to some operator, and this operator has a spectrum. And this actually is it's the energies that you can have in the system. I mean, your electrons, these are the energies that your electron can have when it propagates. And the conjecture is that if you are in some parts of the spectrum, you are localized. So this is the whole point of being a semiconductor, that for some energies, you stay localized, your wave cannot propagate, stays stuck. But for other energies, if you put more energy in the wave will propagate. Okay, so the obstacles won't be enough to stop the wave. And this is what's called the metal insulated transition. And this has also been very studied in the physics literature. And in mathematics, actually, it's one big open problem. That's the biggest open problem in this theory of random Schrödinger operators. So let me just tell you what we know and what is conjecture. I'm going to depends on the dimension. In dimension 1, so when my particles are just on a line, this is a one-dimensional system. There is localization everywhere. So if I think that my electron is moving just along one direction, as soon as there are random obstacles, then the wave stops. In dimension 2, so now I'm in the plane, there is physicists say that it still should be localized, so the wave should stop. But we haven't been able to show that from the mathematical point of view. We can only show that there are some energies for which it stops. We cannot say anything else, and we cannot go. Well, we say localization everywhere in the spectrum. That means for all energies. We actually cannot go all the way in all energies. We can only study some parts of the spectrum. The techniques do not allow to go further. And there is this parameter that I haven't mentioned yet in my function here. This parameter lambda, that in a way allows me to control the disorder. So you saw earlier there was the barriers, the obstacles on this wave that was propagating were disordered. But I can actually tune how disordered I want it to be. It can be a small perturbation of something that is ordered, or it can be really, really wild and put the obstacles really anywhere. So I can talk about small disorder and strong disorder. This is how I can modulate the disorder present in my environment with this parameter. So the transition also depends on the parameter. If I have a small disorder, I would expect it not to break too much the picture. So to be still very close to the uniform case, to the homogeneous case. And to have strong disorder would be to really, really change the behavior of my system. So in dimension 3 and above, there is this conjectured metal insulator transition that is not proven mathematically, except in very, very specific cases. And this transition is that if I look at the spectrum of my operator, which would be represented by this line here, or that line there, or that line there, according to this disorder strength, here in the center, I would have a delocalization. That means that the waves would propagate for these energies, and for energies near the edge, they would stay localized. So you see, we would have this semiconductor behavior here. For some energies, stays localized. For some energies, it propagates. So this is what's the conjecture. What we can study, it's actually that there is localization. So we're very efficient, as mathematicians, we're very efficient at proving that the waves do not propagate, but we're not efficient at proving that they can propagate. This is very hard, and this is open. So in this video, this example, yeah? The dimension. Yes, the dimension of the space, right. This because from no, I don't mean the three-dimensional space. Space can be any dimension. No, these are Euclidean spaces. 4 dimensions. Well, I can have a system with an extra property. I can have a system with an extra spin, and I can add a dimension there. No, in my system, the wave function, yeah, the Hilbert space. Well, where the function lives is it can be any dimension depending on what my system properties are. But of course, I mean, the dimension 3 is particular because we can all understand what 3 dimensions is. But yeah, I mean, mathematics is not restricted to that. And you see that the dimension plays an important role in this transition. Okay, so now, and just to do a little bit of advertising for the Institute, we had, so this theory, the random Schrödinger operators, started in the early 70s. So Anderson discovered this phenomenon in the late 50s, in 58. And then in the 70s, these 3 mathematicians started studying this in Russia, in the Soviet Union. So actually the field is, well, relative as young as these 3 people. And this is Ilya Golsha, Leonid Castor, and Stanislav Molchanov. And they're one of the, the people that initiated the whole theory of random Schrödinger. And we had them here in June. We organized a conference to celebrate the birthday of this birthday boy. This is Abel Klein, who worked a lot on the theory, developing mathematical techniques to prove Anderson localization. And he was turning 75, so he wanted to celebrate his birthday in Cergy. He works in California. Why he would want to come to Cergy from California? Because François was his long-date collaborator, François Germinet. Maybe you have heard his name. He so far the president of the university. He worked a lot before becoming a president. He worked a lot in random systems, and he also developed a lot and made very, very big contributions to the theory of random Schrödinger operators. And he worked a lot with Abel. And Abel loves Paris, loves France, and loves Cergy, so he wanted to have his birthday, which in mathematics, people celebrate when you turn 70, and you have trained a lot of people, and you have collaborated with a lot of people, and you have created a community around you. People celebrate you. When you're 70, 80, and so on. So that was a big thing. And he wanted it to be here. So we did it here at the Institute with Flora and the people in the administration that you see here. They all helped organize this. And well, we had very big names like Svetlana Zhytomyrskaya, who has also received a lot of prizes, and these three guys here who had a great, great time. He actually stayed even longer, still like 2 weeks. Okay, so this is also a reason why we're here talking about random systems. Cergy has had a very big role to play in the development of the theory with François and also other people that worked in mathematical physics back in the day. And now I think I have... Okay, yeah, no, that's more than enough. Now I wanted to tell you something a bit more recent. So this was the whole introduction. And I wanted just to tell you something that we have recently worked on with my collaborators. So there are, so as I mentioned earlier, to prove this transition is extremely hard from a mathematical perspective. So people are always looking at how can we trick the model to induce a transition, or how can we find models that exhibit a transition? Because phase transitions are really, really hard to find, but they take place all the time. And actually, Hugo Dominique Copin, the French mathematician that got the Fields Prize, he showed a transition in the Ising model when in using his probabilistic tools. So this is a very big a driver in a driving force in the community. And recently, there was a connection made where some transitions where people were able to prove transitions. So this is a model, the linearly reinforced random walks. This is a model that comes from probability theory, and in principle it has nothing to do with quantum systems. And this is something that people in probability theory started studying. They have been studying it for 20 years already. These are random walks. Usually, I don't know if you're familiar with the term a random walk, but just think of, this like how you would visit a city. You start doing random walks. You just start walking everywhere without any aim, without any, just pick a direction, walk there, then cross the street, walk somewhere else, just to discover. This is a random walk. Now, random walks, by definition, have no memory, because usually you don't have any preference for the direction that you're going to take. You don't remember that you came one way, so you're not going to go back through that way. All the directions are possible every time, whenever you take a step. But people have introduced what is called reinforced random walk, that is a way of having a bit of memory in your walk. So, for example, let's say you're discovering a new city, and you keep some memory of the walk you're making just to go back to your hotel. So this would be an example of like memory in the random walk. And these processes have very nice properties, very interesting. They have tons of applications. But one thing that is interesting that it's a connection that was made by these people, Sabotares and Zeng, with a model from statistical physics. And that it has a very, very scary name, supersymmetric hyperbolic sigma model. I don't know if Emily is laughing, so I don't know if she knows this. Sigma model, supersymmetric hyperbolic is like everything you don't want to see in one model. But the truth is that despite that, the people that are brave enough to study this, it was very rewarding because this model was introduced to study many particle systems that have a certain spin. But in this case, the spin is not what, it wouldn't take the values that you would expect. It's a bit different. It takes values on a hyperbolic space. Okay, this seems like a real mathematical construction, but it's actually, it actually used to model. It's related to the Anderson model, and actually people studied this in order to understand better the transitions, the phase transitions. And people actually were able to prove, so Margherita Di Sertori, Tom Spencer, and Simbauer, in 2010, they were able to prove that indeed there is a transition for this model between localization and delocalization. Now, this is not exactly the Anderson model. It is related. And people thought, well, maybe this will give us some insight to study the actual Anderson model. And it exhibits a transition exactly as one would expect, depending on the disorder and the dimension. Now, let's go back to the link. There was a link. These people realized that there was a link to this model, and in this model, there was a transition. And they were able to go back to the probability model and show that this model also exhibits a transition. So you see here two similarly unrelated models where what was done for one helped people to understand the other and show a transition. Now here, transience, recurrence, this is how the random walk behaves. A random walk is transient. It's transient is if the walker starts walking and visits all the points in space, and it's recurrent if it at some point it returns to the original place. So when you would be in a city, you would do a recurrent random walk. If you did a transient random walk, it wouldn't be clear that you would arrive back to your hotel. And just, if you're ever around mathematicians in a new city, they always say, I'm going to go for a random walk. This is a joke because we know that in 2 dimensions, the random walk is recurrent. So eventually we are going to, it's transient. So eventually you're going to visit every place in the city if you just do a random walk. This is funny for mathematicians. Okay, so now you see here, I'm talking about 3 models, but here are just 2. So what is the third model here? The third model is in something that is in common. So how they made the link between these two, there is something in common between these 2 models. So for this jump process, it's what's called a mixing measure. It's another function associated to the system. Here in this system here, this what's called the Gibbs measure. These are 2 functions, and they had one element in common, that it was an Anderson model. Not the one that Anderson proposed, but it had a different potential. One term was different, but it's the same class, it's the same family of models. So this appears in both systems. And given that for both systems, people know the transition, well, we started collaborating with Margherita Di Sertori and with Xiaolin Zheng to try to see, well, can all this information about the transition, can that tell us something about this model here that looks like the Anderson model? And just to make things short, because this last slide is a bit more technical, the answer is we don't know yet for the spectrum, but there is one function that is associated to the operator that does exhibit a phase transition. And this is very nice, because this is in a way the first time that we see this for the Anderson, for something that looks like the Anderson model. And this is the function that is called integrated density of states. That usually for the Anderson model has some certain behavior, but for our operator doesn't have the same behavior, which is quite peculiar, but I mean, there is a good reason behind it. And this function exhibits a phase transition that depends on the dimension and on the disorder. And maybe if we continue working on it, maybe we will get something on the spectrum, which would be really nice. But so far, this is not bad. So these are the references in case you're interested. This paper is recent, and thank you for your attention. Thank you very much, Gonya.